All right, so here we are in lesson 6.3, I think, but we're still, again, just progressing through the notes little by little. We're doing the trig proof stuff here, and we're on example number 3. So, example number 3 has got a sine 2x over a cos 2x plus 1. Typically, whenever we have our b value in a question, we want to get rid of those right away. So I'm just going to click over to ye olde formula sheet here. And I can see that sine of 2a is 2 sine a, cos alpha. So right off the bat, I can go, okay, this is 2 sine x cos x. That one looks good. Now the tricky bit is that with cos 2x, there's a couple of potential things I can use. Right? There's 3 of them here. And that makes things a little trickier to know which of those I want to do. So, if we look at them here, that's really hard to erase. You know what? I'm just going to skip erasing it. But if we look at those things here, one of them has a minus 1. And if we look at our original, see how it has a plus 1? We're going to want to get rid of that minus 1 so things can cancel. Currently, nothing can cancel because this is a stop sign. That's a terrible octagon, but that's the idea. Right? Remember, pluses and minuses that aren't contained in brackets are stop signs. Whatever we think we can do, we can't. So I can get rid of it, though, with this one. I'm going to pull this one in, my 2 cos squared x minus 1. So this part here becomes 2 cos squared x minus 1. And then I've got this part that was already there that was a plus 1. Now, since nothing's multiplied by the brackets, I can now just remove my brackets. And removing these brackets allows me then to go 2 sine x cos x. My minus 1 and my plus 1 cancel off, divided by 2 cosine squared of x. And now I can cancel 1. Now that I've gotten rid of that plus, now I can cancel some stuff off out of here. So this cos can cancel with one of those coses, and this 2 can cancel with this 2, leaving me with sine x divided by cos of x. And hey, look, that's tan x. I made it. Right? Because my right side was already tangent of x. So now I can write left side equals right side and throw a bam down there. Okay, again, remember that's just for informal. If it was a formal thing, you'd write therefore QED or just left side equals right side. But we want that good release. All right, here's the next one. 1 over 1 plus sine is equal to secant x minus sin x secant x over cos. Hopefully we can spot that the right side is more, looks like it's more complex. So instead of working more with the left side, I can just go straight over to the right side. And what I'm going to do here is I'm going to first do my NPVs because they asked me to. I see that there's a secant. Secant automatically has the non-permissible values that x cannot equal pi halves plus pi n. Again, that's just because secant. We also have some situational stuff that we've got to work with in this one. We see that cos x can't equal 0 and sine x can't equal negative 1. Now, where's cos 0? Well, on our unit circle, that's just there. So that's still pi halves plus pi n. We've already accounted for that non-permissible, so we don't need to re-account for it. And then we can also go sine x can't equal negative 1. Well, that just happens down here. So we've already got that accounted for in there as well. So this then is our total non-permissible value statement. We don't need to say anything else from that point. Good? All right. Hopefully. Now we're going to move on to actually solving this thing. So I'm going to take this side apart. On the right side, and if we wanted to, one of the things people often do is they default to just change everything to sine over cos. or sines and coses. And that's a good strategy, but it's not always the fastest way. So what I'm going to do is I'm going to first factor out the secant x. This is going to give me 1 minus sine x. So I just see that as a common factor. Now, a secant x in the numerator is the exact same as a cos x in the denominator, so I can now make this 1 over cos x times 1 minus, let's just do this here, 1 minus sine x all divided by cos x. And now when I multiply this through, I get 1 minus sine x divided by cosine squared of x. Hopefully that's all reasonably good, reasonably straightforward. Okay, so now we just have to go from here. Cos squared x, whenever we see something with a squared, we should think, you know what, I can hit that with a hammer. So I'm going to go 1 minus sine x over 1 minus sine squared of x. And again, now we're so close to getting out of this raptor cage that we can basically taste it. All I have to do now is difference of squares my denominator, right? So 1 minus sine squared, hey, that looks familiar, I'm good with that. I can just change that to 1 minus sine x over 1 minus sine x, 1 plus sine x. So the 1 minus sine x's cancel. I'm left with 1 over 1 plus sine x. And hey, what do you know? Look, solved, proved, done, good to go. All right, moving on. Got to keep moving on. Left side equals right side, and we're ready to rock. Now this next one, there's a lot going on here. Now, this one they didn't actually ask us to state our non-permissibles, and to be honest, I'm a little disappointed because this is a great question for them to ask us that, because our non-permissibles are not just the standard ones that we've been dealing with. So we're going to do our non-permissible values on this one too, just not to show off, but to make sure that we really know what we're doing and we can see all of the potential things that could be happening to trip us up here along the way. So I like this one a lot. This one as well, I wouldn't say necessarily that either side is that much more complicated than the other. I think we could make it a good case for either one being the place where we want to start. Now, I'm going to start on the left because my sine 2x, when I find those double angle things, they're typically ones that I want to go through. Now, I'm losing my track of thought. I said we're going to non-permissible, and then I just went on without it. So let's NPV this thing really quick. My NPVs, there are no numerator things, or there's no built-in precursors. I don't have secant, cosecant, tangent, or cotan to worry about. But I do have some interesting situations. So right here I can see that 2 sine x plus 1 can't equal 0, and I can see 4 sine squared of x minus 1 can't equal 0. This thing we should hopefully see that it factors to 2 sine x minus 1, 2 sine x plus 1. So my non-permissibles are such that sine x can't equal a half or negative a half. Now, again, that's not a non-permissible. I can't say what sine can't be. I have to say what x can't be. So x is not going to be equal to either anywhere where sine x is a half and negative a half. On the old unit circle, that's literally all 4 corners of that reference angle, and that's my pi 6. So my NPVs is x cannot equal pi 6, 5 pi 6, 7 pi 6, and 11 pi over 6. So there's lots of little NPVs there. And again, they're not our standard NPVs. If we wanted to general solution those, we would again just put plus 2 pi n in all cases. All right, so now that we've dealt with our NPVs, now we're going to go to solving this thing. Again, typically when I see a sine 2x or a cos 2x, I'm going to try and work with that side first. That's just my habit, certainly not the way that we have to do things, but I'm going to start with this side. So I'm going to turn this into my double angle identity, which is my 2 sine cos. So back to here, that's just going to become 2 sine cos. Well, and again, I'll be formal with these. Sine x cos x minus cos x, all divided by, and I already saw that I can factor this as a difference of squares, so I'm just going to do that right away. And that gets me to here. Now, I can see that I can factor out a cos x, so I'm going to factor out a cos x of my numerator here. And that's just going to become 2 sine x minus 1, all divided by, I've got a little bit extra bracket going on there. Let's take care of that for me. 2 sine x minus 1 and 2 sine x plus 1. I can now cancel off my 2 sine x minus 1s, and I'm left with cos of x over 2 sine x plus 1. And sorry, the brackets are up front there. So that's what that looks like right now. Now, I'm actually pretty close to my destination. This is looking pretty good. But instead of trying to make it more complex, I would go, you know what, I think I simplified that as much as I can. I'm going to leave that as a spot. Again, you could go either all the way from left side to right side, or all the way from right side to left side, or we could go partway down on both sides. All of those 3 techniques are considered a valid proof. So what I'm going to do on this side is I'm now going to take this part apart. I can see that there's a cos x as a common factor. So I'm going to factor out a cos x. And hey, look, some great stuff is happening right now. 2 sine x plus 1, because we see this and we think, wow, I could hit that with a hammer. In fact, that's my really nice hammer. That is just my basic sine squared plus cos squared equals 1. That's my start of the course, start of this unit Pythagorean identity. So this whole thing is just 1. So now I'm just at cos x times 1 over 2 sine x plus 1, and bada bing, bada boom, there we go. Left side equals right side. Happy, happy. Okay, so now I'm going to move on here to this next bit. Oh, we're already into the check your understanding. I will do a video with all the check your understandings in a little bit, but right now I'm going to move on to the next part, 6.4, which is solving, solving equations using identities. Now, this is back to the equations, not an identity. Now, equations, remember, have solutions. They are valid only for some values of x, not for all values of x. So I'm going to carry through here and find the solutions. Again, we can always do these graphically, right? We can always verify our solutions graphically, and that's a really useful thing to do. You can even solve it graphically first, and then show some work that gets you to those same answers. I don't care as long as you have both techniques, which technique you did first necessarily. So, the only difference here is that we can't just solve these algebraically right off the start. And look at this, I'm like, wow, there's nothing I can factor, I can't combine those things in any way, shape, or form. However, I see sine of 2x, and in my head, I'm like, wait a sec. I know you, sine of 2x. You are right here. You're just 2 sine cos. So right off the bat, I can write this as 2 sine of x cos of x minus cos of x equals 0. And again, just like when we went through the equation solving back in chapter 4, we need to remember that we can't cancel stuff typically. We have to be able to encounter it as we go. So I'm not going to try and add cos and cancel. What I'm going to do instead is factor. So I factor out my cos x here, leaving me 2 sine x minus 1 equals 0. And now I can solve each of these factors separately. So cos x equals 0 and 2 sine x minus 1 equals 0. So cos x is 0, again on my old unit circle. Cos x is going to be 0 right here. So pi halves and 3 pi halves. And again, we're on a limited domain, so we don't need the general solution. In this question, it's always key to focus on what domain the question wants. All right, next up is 2 sine x minus 1. Here I'm going to get sine x equals positive a half. And if sine x is a half, that means I'm, again, on my unit circle here, I'm right there and right there. My 2 positive values. So that's just going to be x equals pi 6, 5 pi 6. Bada bing. Done. Now let's just show this graphically. If I was going to do this graphically, I would just bring out good old handy dandy super trusty math TI-83, and I'm just going to type this in. It looks like I was already solving this one in class, so I've already got it set. Sine of 2x minus cos of x, and now I'm just going to plug those values in, or just graph it straight. I'm going to look for my x-intercept. So there's that. My x-intercept, I'm just going to go second calc 0. I'm going to check here first. Left side, right side, guess. So there's that value. Now again, we've got our handy dandy trick. We go second quit, type the x, remembers that value, divide out our pi. Oh, let's clear that. So x divided by pi gives us that number, and then that number we can math frac to get pi 6. So we can put that pi 6 back in. 1/6 times pi that we factored out, so that's our pi 6 solution. If we wanted to check them all that way, we certainly could. Go back to the graph, find the next one, second calc, not intersect, 0. Come on, McManus, stick with the program here. So I'm going to go now between 1 and 2. Looks like it's about 1.5, which is a good sign. It's about 1.5, should be about pi halves, right? So now we go second quit. Hit our x, divide by our pi, and look, it is, it's pi halves, yay! So we've now found this one and this one. Now, just in the interest of time, I'm not going to continue going through this process, but I feel confident that you guys are all super calculator jockeys and you can ride your calculator through the end zone on these ones as well. Okay, next one up. Here we have a sine squared and a cos. That's awkward. That's not going to get me anywhere I want to go. Remember back to chapter 4 when we were dealing with those equations, solving equations where they're in sort of 2 parts. We could solve those equations only if we could factor it. If it's not a factorable quadratic equation, then we just can't work with it really. But we're going to factor this thing. I can't factor right now, though, because I have sines and coses. Now, thankfully, we have a way of turning sines and coses into each other. I can't change the cos into sine. However, pardon me, sine squared I can change into cos. Because, again, if we think about this, we have our sine squared plus cos squared equals 1. That's our hammer. That's our basic Pythagorean identity right there. So I'm going to go cos squared equals 1 minus sine squared, and I'm going to replace this 1 minus sine squared with cos squared. So 2 cos of x plus cosine squared of x minus 3 equals 0. I just brought the 3 over to the other side as well while I was at it. Now, again, if I really wanted to, I've talked about putting that costume on it, right? Let's just call this C. And if I just do that without describing it, I can't do that. That wouldn't be counted for points on a diploma. But if I do this magic little statement allows you to define a variable any way you want. So let cos of x equal c. Well, then I can go c squared plus 2c minus 3 equals 0. And then I have c plus 3. By factoring by inspection, I need to make a positive 2 here. And c minus 1. So that means my cosine of x is going to equal 1. And my cosine of x is going to equal negative 3. Now, cos of x, that's a good one. Cos of x equals 1. That happens at 0 and 2 pi. Not pi. It's negative 1 at pi, but at 0 and 2 pi. Now we check our domain, which I have to scan back up here, is including 0 but not including 2 pi, right? Including 0 but not including 2 pi. That's what the equal sign there means. So I need this one, but not that one. Not in my domain. And then this thing here just has no solution, right? There is no value for which the cosine of that value equals negative 3. It just doesn't exist. Cosine's outputs, cosine's range, is limited between negative 1 and 1. So negative 3 is outside of that domain, outside of that range. It doesn't work. Now, we could also see that if we imagine this graphically, you're like, I know cos x, I know that graph, yay! And then negative 3 is just down here. So it's apparent that it's not a part of my solution set. Or there are no intersections, no solutions there. Again, thinking about it graphically. So my only solution there is 0. Next up. Okay, so this thing here, sine squared plus a half tan cos. Solve it algebraically, and then they want this one in degrees. Again, back to that last question. Definitely solve using your calculator. Just in the interest of time, I am skipping that step and letting you guys ride your calculators to the end zone on your own. But please do try that, verifying those things graphically for all questions, whether it says to or not. Okay, sine squared of x equals 1/2 tan x cos x. Right off the bat, I'm going to go sine squared of x equals 1/2 sine over cos times cos of x. Now, as we've already described, canceling things out of these is very troublesome. We cannot cancel things typically, but I'm going to do it anyway. Now, one of the things that I had to do to cancel that is I had to do my non-permissibles. Without even describing it, I mean, cos x can't equal 0, which means that x can't equal pi halves, 3 pi halves. We already saw that, or actually let's degree this since we're in degrees. X can't equal 90 or 270. Now that's important to note because when we're solving, we need to check our answers against our non-permissible values, if there are any. So now we get this. Sine squared x equals 1/2 sine of x. And now we can get very, very tempted to just go, oh, cool, sines on both sides. Let's cancel one of those out. Sine x equals 1/2. Yay! Except we have just gone down that dark alley. We've just taken a shortcut that is not mathematically allowed. To remember why, let's think back to Math 20-1. We have something like this, x squared equals 4x. You could say, I can just cancel off x and get x equals 4. But the correct way to deal with this is we go x squared minus 4x equals 0, and then we factor out the x. So x cannot equal 0 or 4. So when we just solved it this way, when we shortcutted, we lost a valid solution. We lost a valid solution that we would have needed to incorporate. So let's ignore all that schmoz. And again, our instinct, our reaction should instantly be just to bring all of our terms to one side. And now I can factor out sine x as a common factor. Sorry, sine x minus a half. Look at me go. Where am I going with my common factoring? Sine of x minus 1/2. So sine of x equals 0 and sine of x equals 1/2. Sine of x is 0 at 0 and 180 and 360, but 360 isn't part of my domain. So 0 and 180 is there. Sine x is going to be 1/2 on yield unit circle here and here. So that's going to be my 30 and 150 degrees. And now again, checking this graphically, what I'm going to do is I'm going to go into here. Sure, whatever. Y equals, and remember, when we write sine squared x, that's just us being lazy. What we really mean is that, let's delete the rest of that there, equals 1/2. Now again, if you have the fancy TID4, you can do that whole all right, so got that part in. And again, if you got the fancy TI-84, use the fraction template there. Maybe I already said that, losing my mind, but that's okay. Now we can just graph this. Oh, let's again make sure we're in degrees. And then we'll just make our window settings exactly equal to our domain that we want to deal with here. So from 0 to 360. It would be really handy if our scale was 30. So let's just do that. And then that should be about it. So there's my sine squared graph. And there's my weird tan cos graph. And now I can just find my intersects. Sure, yes. And there's my 150. Again, I can see it's kind of in both places here, but we'll just assume that we can get the rest of that out. So if I drew this out here, I would have something like that, and something like that. And so my solutions are 180, 150, 30, and 360, except not 360 because it's not in the domain. All right, moving on. Oh, I should throw some axes on here. So this is 1, -1, and then, yeah, close enough. All right, find the solution for this thing. Cos cubed over sine equals cotan over the interval from here. So right away I want to just change my cotan into coses and sines. So I'm going to go cosine cubed of x equals cos over x divided by sine over x, sine over x. And again, even though they didn't ask, I can note that sine x can't equal 0 because it's in the denominator. Now, if I've got the same denominator in both places, I can basically just cancel off the denominator. Or if I just multiply both sides of the equation by sine x, now I can just cancel, 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 and I get cos cubed of x equals cos x. Now surely I could just divide out cos x and get cos squared equals 1, yes? No, that's that same trap. Don't go down that alley, right? So cos cubed x minus cos of x equals 0. Now we factor cos of x times cos squared of x minus 1. And now a little difference of squares action. So cos x times cos x minus 1, cos x plus 1 equals 0. And I get cos x equals 0, cos x equals 1, and cos x equals negative 1 are my solutions for cos of x. But now we have to put those into trig, right? So we need to see, where is cos x 0? Well, on my unit circle, cos is 0 there. Pi halves, 3 pi halves, except in degrees. And they want a whole lot of solutions here. They want my positive 360, and they want my negative 360. So I'm going to have 4 solutions in here to deal with, which are going to be 90, 270, negative 90, and negative 270. Okay? Where's cos equal 1? Well, that's going to be just right here. And whereas cos equal negative 1, that's going to be right there. Now, again, I'm going to see a bunch of these. And remember that because of the square brackets, my 360s are included, which is important for this, right? That's a solution there, and that's a solution there. So that means that my solutions are going to be at 360, 0, negative 360, and then 180 and negative 180 for a grand total of 9 solutions, I think. 9 solutions. Again, this is a pretty good thing to check. That's not what I want to do at all. Move that back down. This is a pretty good one to check graphically, just to even see if I have the right number of solutions. So I'm just going to go to here and make that cos, or sine cubed. Make this cos cubed. Cos cubed divided by sine of x. I don't think any of those are non-permissible. Are they? Sine x can't equal 0. Oh yeah. Hell. A whole bunch of these are non-permissible. Oh. Right? All of these solutions are non-permissible. Yikes. Anyway, let's see what that looks like graphically. So now if I was to do cotan of x, I'm just going to do that as 1 divided by tan x. You could also do it as tan over, or cos over sine. That would work as well. Now if we graph this, there's my cotan graph. It looks a lot like the tan graph, just kind of backwards. So we can see there's lots of solutions there, but if we go looking at, for example, 0, let's look at our table of values at 0. See how there's 0 isn't a solution, it's a non-permissible value. So all of those 4 solutions just aren't a part of my domain. Now again, if I make this like negative 10 and positive 10, I think I should be able to see those solutions coming online a little smoother. But again, you've got to be willing to check them against the algebraic, or from the algebraic forward. So it looks like 270 and 90 are my only true solutions. Interesting. Now again, your table settings, this is a really handy trick. I can go into my table settings and I can put my table, my change in table at like 30. Right? Now if I go to my table, I can see my values right on up. Oh, shoot. I've made my calculator lie to me. When I went 1 over tan, stop that. When I went 1 over tan, that was actually a bad choice because tan has its own domain limitations. I should have changed it. Oh, come on, stop. Finish up already. So if I change this to cos over sine, that's going to show me that those values actually do work here. So 90 is a true solution to the equation. Oh my goodness. That one almost got me. Example 4. Algebraically solve each of these two things. So cos of 2x equals cos x. Again, I'm going to flip this. But remember, I've got 3 choices for cos. Which choice do I want? I want the one that has only coses in it. Because when we're solving a trig identity, we need to have only one kind of ratio. So it's going to be this 2 cos squared minus 1. So this one's going to turn to 2 cosine squared of x minus 1 equals cos of x. Bring everything to one side. 2c squared minus c minus 1 is 0. And that's going to give me a 2c plus 1 and a c minus 1. Check that out. Negative c, positive c. Yep, all good. So cosine of x equals negative 1/2. And cosine of x equals 1. This is going to happen here and there. So 2 pi thirds and 4 pi thirds. And again, each of these plus 2 pi n. I can't combine them because they're not like on 180 or not on a straight line. Cos x equals 1, though, is going to happen just up here. Right? So cos x equals 1 is going to happen at just 0 and 2 pi. So just 2 pi n. Now, if you look at this, do I want to show you? Yeah, I will. See how these are each 120 apart? I could just go 2 pi thirds n, and that encompasses all 3 branches of these things. But again, that is not a regular occurrence. Throw down your NEI or NE. That even feels strangely right. Okay, next up. This one here, we're going to go 3 cos x plus 2 equals 5 over cos x, right? So I just flipped my secant into 1 over cos x. Now I'm going to get rid of the denominator by multiplying everything by cos x. You can even think about like cross multiplying. That's the word I'm trying to make in my head. But anyway, 3 cos squared of x plus 2 cos x equals 5. And now I'm going to bring this over to the other side. Now we've got to factor this using our decomp or just in our head. We need 2 things that are going to multiply to negative 15 and add to negative 2. It's going to be 5 and 2. So I'm going to go 3 cos squared of x plus 5 cos x minus 3 cos x minus 5. That's going to give me 3 cos x plus 5 and cos x minus 1. Now remember, that means cos x equals 1 or cos x equals negative 5 thirds. Because negative 5 thirds is greater than 0, I can basically just, or greater than 1, sorry, I can just ignore that. That's not going to have any solutions. Cos x equals 1, however, does have solutions. That's going to be at 0 and 360. So that's my solutions right there. So 0 and 360 are my only solutions.